Good afternoon, everyone. In this video, we're going to take a look at the Zifnu 107mm RGB LED Development Module. First, we'll just take a look at the dimensions of the board. As the name implies, it is 107mm by 107mm. The mounting holes in the corners here are M3 and they're on 100mm centers. The location of the LEDs is on 90mm centers, and that's basically 45 from the center point of the board out in each direction. To make it easier for you to use this light module in your own design, you'll be able to download an SVG template to actually incorporate into your designs that has the proper locations for all the LED lens and for the mounting holes. We're going to take a look at the design of the board and the major components, which would be the power input and selection, the DC to DC boost regulator, the logic, which is the microcontroller, and the LEDs. And we'll take a look at the headers and everything as well. A few things to keep in mind as we go forward is the board is designed to be minimal as far as the power usage, since we designed it to run on 4 AA alkaline batteries. It can run off other power sources, which I'll discuss in a minute. But to keep the power usage low and ensure months of normal use of, say, 15 minutes a day if you're using this nightlight or longer, and also months of standby power, we had to keep the components minimal and also be very selective in the components we chose to ensure that the draw was actually minimal. This is a simplified schematic of the development board, getting used for illustration purposes. First, you'll notice you have 2 power input options. The first is via the battery input, which is via the battery connection here, and we have a USB breakout here. This is the other power input. The power switch chooses between these two. You have 2 reverse polarity protection diodes, one going directly into the DC boost converter and another one going into the logic, which is made up of the micro and the infrared receiver. This will become apparent as to why in a minute. First, we're going to talk about the DC to DC boost converter. This is a micro 2876 DC to DC boost regulator. It has 2 major features. One is a bidirectional load disconnect, and the other is an auto bypass feature. Now, the load disconnect ensures that when this device is turned off, which means enable is low, there is no voltage or current seepage either direction, which is important for basically segmenting these WS2812Bs from the circuit when they're not in use, when it's not on, basically. So they draw quite a bit of current even in standby because of the internal circuitry. So in a standby state, when the processor is asleep, only the processor and the infrared receiver module are actually drawing any current, and this gives us a greater standby time of months, actually. Now, the auto bypass feature of the DC to DC boost converter means that when your V-in is greater than the V-out, it actually turns off the internal circuitry and just lets the voltage pass through. So it saves you a bit of battery life as well. And that's only if the enable is high. So if it's enabled and the voltage is higher, it allows that voltage to pass through without using the internal boost circuitry. So let's use an example of where the voltage is, say, 3 volts input on the battery. The voltage there, the diodes used here are roughly a 0.45 drop in voltage. So 3 in, you're going to get 2.55 input, which is plenty for the DC boost and also for the micro and the IR receiver. So in its off state, enable will be low, the processor will be asleep, and the IR receiver will be waiting for a command from the remote control. Once a command is received, it waits up the processor to process the code and to see what code was actually transmitted. If that was the power code to turn it on, it then powers up the DC to DC boost converter circuit, and since we have 3 volts in, it'll actually turn on the internal circuitry to boost the voltage up to a constant 5 volt output. And that'll actually power up the LEDs. And this diode here, once this rail goes up to 5 volts, It'll be higher than this side, which is 3, so this diode will keep the current from flowing and your circuit will be powered, the logic section will be powered off of the boost converter. Once it's powered up, the data will be sent to the LEDs to display the color that was last chosen or the default color. Second example, use 6 volts on the input. 6 volts is flowing through to just the micro and IR. It drops down to 5.55 roughly. And once you actually hit the button on the remote to turn it on, the enable line would go high, turning on the DC to DC boost converter. Now you have 6 volt in, you want 5 volt out. Sorry, you have 5.55 in, you want 5 volt out. So to actually leave the circuitry turned off internally and just pass the voltage through onto the LEDs and also onto the micro and the IR. As mentioned before, this is intended as a development board. The most obvious use, of course, is to develop your own firmware for it and learn how to code, add functionality. And you can actually use our base code, and there'll be tutorials on how to augment the base code and also how to write your own code. If you want to have the LEDs flash in sequence, or if you want to augment the hardware to add a new signal in and have the LEDs react to that, that's all possible with the board. Let's talk about the hardware for a second. So we have a few headers here to give you a hand to make it easier to actually augment the board to add your own hardware to it. The first is a USB header. Now the microcontroller has integrated USB functionality. The default firmware does not have a USB stack, so it is not enabled by default. You'd have to add a stack in, which there are several open source ones available, and if we have enough demand and enough interest, we'll put a tutorial together on how to do that and use one of the open source stacks to do some basic interface things with the board. Second here we have power, VCC and ground, and also VREG and ground. Also duplicated up here by the 12x12 prototyping area. VCC and ground is your standby power directly from the battery. The VREG and ground is from the boost regulator circuit. So it's only enabled when the micro has turned on the boost regulator circuit, as we mentioned in the prior section. This is the in-circuit serial programming interface, which is how you update the firmware. To do that, you will need a programmer such as the Microchip PitKit 3 or a similar programmer. There's many clones, there's many open source programmers. It's whichever one you're used to using. If you don't have one currently, I would highly recommend the PitKit 3. The unused I/O on the microcontroller has been broken out to the I/O header here. RC0, RC1, RC2, RC3, and RA4. Like most microchip products, the microcontroller has dual purposes or multiple purposes on each of these pins. So you can use each of these as a standard input-output. You can also implement them as analog inputs, PWM outputs, interrupt on change inputs for buttons, etc. The best way to interface if you have to have a lot of data moving back and forth, or if you want to control this board from another one, is to actually use either SPI or I2C. And it can be a master or slave setup. So you can actually write some firmware to use the board as a slave device and then use something like a Node MCU, Arduino, or anything else to actually control the RGB light board. Along with the design files for the PCB itself and the layout, you'll also be able to download a template for a daughter board, which you would actually attach to it with a simple 0.100 header. This one is about as small as possible just to demonstrate the smallest size. We can actually take it and extend out as much as you need. Now, the daughter board there probably looks a little bit small in comparison to the rest of the board. So just for comparison, this here is a little ESP8266 module, which also leaves plenty of room on the board for a little bit of level shifting and regulation to bring it down to 3.3 volts from the 5.